Okay. Anybody having trouble with that? You'll know that you're supposed to come with a knowledge of kinetic and potential energy. Okay? So y'all should have already learned the difference between the two. Who's great on that? Thumbs up. Who's in the middle? Who is a negative? All right. That's why I did this today. What's up, Janie?
I have a question on one of them.
Okay.
A girl's swinging and she is at the highest point of the swing. So is she swinging or is she stopping at the highest point of the swing?
Oh, I don't know.
Is she continuing in motion? Like,
Well, there's a little secret that you got to recognize there. I don't know if you recognize it or not.
she stopped. No, it says she is swinging, so she's still in.
Okay. A slingshot that has been pulled back but has not been let go. Is that potential or kinetic? Why is it potential?
Because it has the potential to be moving.
Okay, yeah. Potential is exactly what the most simple English that you can think of. Potential. If I say, y'all all have an enormous amount of potential. Like, I think that you have a lot of ability, right? Does that mean that you've done it yet? No. So that's the difference between potential and kinetic. Potential is it's waiting. Kinetic is it's moving. Okay? Okay. So, a slingshot that has been pulled back but not been let go, that is potential. Put a little P on the back of it. You should have 10 that you cut out. A bobsled is moving at its greatest speed around the final turn. Kinetic. Little k. Not necessarily lowercase. We're just putting it small so that you can't see the answer. So when you study them, okay? A grasshopper reaches the highest point in its jump from one plant to another. Ooh, who says potential? Who says kinetic? It's potential. Okay. Let's talk for a second. Jane, I know that you've been double bounced on the trampoline before, right? And I'm going to use the example of double bounce because it's way more obvious. You know, whenever you fly up and you get that split second where you feel like you could just like run in the air but you don't go anywhere, you know what I'm talking about? You just fly and you just have that second where you kind of like hang. That's potential energy. And what's happening is you're actually changing direction, but to be able to change direction, you have to pause. Does that kind of make sense? Because I was going this, pause. As soon as I go down, kinetic. And I'm gaining kinetic as I fall. Does that make sense?
So when you fall, you have potential. Before you have potential, but then when you go the other direction, you get negative.
No, it's like potential, kinetic, potential, kinetic. But when the trampoline pulls you back down, like you know how whenever you land and you're like, you know how it almost feels like you're pulled in the bottom of the trampoline? That's potential again. Makes sense? Because as soon as it lets go of that, your direction is going up. And as soon as you start to go up, your kinetic is going up. Okay? So, the grasshopper reaching the highest point, that is potential. A girl is swinging and she is at her highest point of the swing. Potential. Hey, guess what that's like? Newton's cradle, and I'm going to pull him out again in a couple of days. Okay, and we'll talk about that again. So that girl swinging is potential. A cliff diver is just about to jump off an 18-meter high cliff.
Potential.
Potential. I said cliff. A baseball has reached its highest point after being hit toward the top of the stadium.
Potential.
Yep, potential. A satellite that is orbiting the Earth at nearly 20,000 miles per hour. Kinetic. A skydiver is traveling at his fastest speed, which is his terminal velocity, when falling. Kinetic. A basketball sits on the rim before falling into the hoop. Potential. An arrow is released from a bow and travels toward the target. Kinetic. You would reach terminal velocity faster in the yes. All right, let's do our notes. I color-coded with blue, green, and purple today, but you also need your pencil and a calculator. Nope. And you can always go back and color code at home, too. Okay, y'all, what's energy? Look, right now, if I'm just talking to you about it, I might not expect you to have the science to go with it. Just in your mind, what do you think, what do you relate whenever you hear the word energy? Like, what do you think? You think of the sun, okay. Moving, okay. Janie, what makes you think of the sun?
Because the sun produces like a lot of energy. So like for solar panels, that's why they have solar panels to absorb some of the energy that the sun gives out.
Yeah, the sun is like the main. It like drives all living. It drives everything. Like, I don't know. It's like it makes living things live. It makes like it controls like how things cycle and flow, and yeah, the sun is like the major driving factor of everything. But
Have the sun, have all of these and then we all like.
what do y'all think that you need energy for?
Power stuff.
To power stuff? To do something? Okay.
To move, to produce movement.
Okay. Yeah, that's good too. Energy, by definition, is the ability to do work.
That's what I'm saying.
That's what you're going to say?
Yeah.
Okay.
Because I remember that definition from somewhere else.
Okay.
Even I remember.
Well, tell me, what's work?
Work is really doing something like you. Work is harder to do because it could be a number too.
Are you doing work?
Yes.
We're running. Is homework work?
Yeah.
Is studying work? Is
You're doing something, as long as you're not.
what about whenever you pick up your clothes or that's work?
You're using energy. You are. Work.
movement work? It depends. Okay, let's talk about work. Work is when a force is applied over a distance. Okay? So think about this. Here's my force. Is it over a distance?
It's the distance between the thing and the button.
Is this work?
Yes. It's applied over a distance.
What if I made everybody stand like this the whole hour? That's work?
No, that's not work. Well, I think there's work.
You would be pretty darn tired, huh?
Yeah.
Guess what? It's not work.
You're not moving it anywhere. It's not going any distance.
I mean, it probably wouldn't have been except for them shaking.
Yeah, but it's not work.
It's not.
So I have to move it. The force has to be the same direction as, like, to do this, the force is up and it doesn't move a direction. So it's not work. Your backpack could be so full and heavy as can be, but this is not work to carry my backpack. Because the force on it is up, but what direction does the backpack move?
It's moving forward.
But do you see what I'm saying? The direction the backpack's moving. But the force is, they're not the same. That's not work. No, you don't have to sweat to do work. Because maybe you would start to sweat if you had a really full backpack carrying it like this, but you're not actually doing work. If you take the backpack and you do this, or this, up or down, that's work.
You have to move it.
You have to move it. The force has to be in the direction that it moves.
Where's the force? So pushing the backpack and
Yeah, you could push the backpack. You could drag the backpack and you're doing work.
yeah, because
Does that make sense? Okay, so to have the ability to do that, you have to have energy. Does that make sense? Because the only way I would be able to get that force is to have energy to be able to apply it. Does that make sense? That's where it comes from. Okay? I'm not necessarily going to grade you on work. It's just, does it make a little bit more sense now where energy comes from and what it will as we go. Okay? There is an SI unit. There's always an SI unit. Joule. It's after James Prescott Joule. He's and it's a capital J. Okay. Now I used green for everything with potential energy. So if you want to color code, you can. Or you can go back and do that later. Okay? I'm just letting you know I did green. I'm going to write in black. You can write in green or whatever, but so you can see it. Potential energy, the first type of energy we're going to learn about. This is energy an object has due to its position or shape. And they also call this stored energy. Because if it's stored up, then it's just waiting to be used. Does that make sense? There is, but you don't have to know the formula for this one, so I'm not telling it to you. Yeah, when your Christmas stuff's stored in your attic, it's up there and it's waiting to be used. That's a good example. Okay, now we have 3 types of potential energy. The first one is gravitational potential energy. So what do you think that has to do with?
Gravity.
Duh.
The joy.
The energy, stored in an object due to its vertical position or height. Well, I see what you mean, like by that it means that he would be moving, but what is actually causing him to move is the gravitational, what's happening is his gravitational potential energy is being converted into kinetic energy. It's a little bit more advanced, but we have to learn that too. Okay? But gravity is what's pulling him down, so because of how high he starts, that will tell you how much gravitational potential energy he has. Yes. The formula for potential, you don't have to know it.
Why do we have to know about kinetic but not
I don't know the answer to that question, Janie. I'm just following what they said that you have to know. Okay? Okay. Elastic. Do y'all know what elastic is? Like a rubber band. Yes. Stretchy. Yes. So this is energy stored in elastic materials due to their stretching or compressing. So yeah, a spring, a rubber band, yeah, rope will stretch until it pops. Like tension. Yeah, this has to do with tension. Very good. Okay, the last one is chemical. Stored energy due to a chemical change. And we haven't talked that much about it, but I did teach it to you when we learned about bonds. Do you know what a chemical change is? It's when something becomes a brand new substance with different properties. So y'all have said some: rust, fire, explosion. No. Smoke is like a byproduct of the reaction, but these are from chemical reactions, chemical changes. Food rotting. Your food, when it gets digested in your body, that's a chemical change. Your body, inside the food are all of these different atoms, and they're waiting for you to use them. And if you don't eat, you are weak. Right? Do you get what I'm saying? Well, eventually, but still, if you don't have the proper nutrients, then your body cannot use them as fuel. That's what this is. But it's a chemical reaction for your body to use them. So, right now, before you eat them, it's stored, it's waiting. Then your body's going to react inside your stomach and use them. And then that's kinetic. Okay, does that make sense? Okay. Gosh, that's dissolving though. Yeah, no, let's not go there. Okay. Okay, these two guys right here. What do y'all think about their potential energy?
The guy on the top, he has would be potential because he's not about to go. He's about to get in.
So they don't both have potential energy?
They both have potential energy.
Okay, they both have potential energy, but this guy right here has more potential energy. Why?
Because
He's higher. So if we had another guy and his slide was up here, he would have even more. The higher you are, the more potential you have. Okay, so this guy is less potential. Sorry, it looks like a V. It's an R. Yes. So, higher. And that's because of gravity, right? Does that make sense? That would be because of gravitational potential energy. The more height you have, the more that gravity is going to pull. What if I had two objects that have different mass? More mass has more potential energy. It's not that it's more gravity. It's that it has to do, it's almost like momentum. Like how they're going to gain so much motion because they have so much mass. You know what I'm saying? Like when they hit you, they're going to have more of a punch than, yeah, like the big, yes. It will put, I mean, yeah. Kind of two. Okay, what about more tension or compression? Like, look at this versus that. This has more tension, so it has more potential. And then the harder I would press a spring, the harder I compress the spring, the more it will pop up. Okay, kinetic. I used purple if you care. I don't care. Kinetic energy is the energy of motion. Very simple. Okay, down here we have examples of kinetic energy. What's the first one? What kind of energy is that? It is kinetic, but what would they call it? Sound energy. Do y'all know how that works? Huh? Okay, I'll give you the example of like how we can hear each other talk. Okay? Inside by your vocal cords vibrate, move, motion, that which hits the air that's right there. So now the air particles are moving, which then hit the air particles out here, right? There's air particles in front of that too. So then they hit the next set of air particles, which hits the next set of air particles, which hits the next set of air. And so sound travels by pushing its way through the air particles. But all of that is motion, so it is kinetic. Does that make sense? Okay. The next one. A light bulb. It's not electric. Do you know what it is? Do y'all know what light is? It's called radiant. We're going to explain how this moves later. Okay, can you see the next one's a flame? What do they call heat energy? Nope. Thermal. Thermal energy is heat. So, how would that be motion? Do y'all know how heat moves? Heat moves from hot to cold. Actually, in physics, there's no such thing as cold. They say that cold is an absence of heat. Yeah, that sounds weird, huh? Makes sense? So, take your hand and touch the table. It feels cold, right? Yeah. What's happening is, the reason why it feels that way is because the heat is leaving your hand and going to the table. So you are left with no heat. Does that? Huh? You were telling somebody that, yes? Uh-huh. Yeah, it's measuring, like, it's how fast the particles are moving. So what happens is, in some, like my coffee, okay, the particles are moving really, really, really fast, but there's particles around them that are moving slower. The fast ones give their motion to the slower ones, and then eventually they have the same speed and they're the same temperature.
So, is that how steam is?
No, steam is a vapor. The Yeti cups have such a good material inside of them, they do not let the heat, if it's cold inside of it, then they do a great job at not letting the heat come in. If you're drinking something hot in your Yeti cup, then they do a great job at not letting the heat go out. Does that make sense? Okay. And the last one on here is electrical. So, when you have a wire, like, okay, the wire in the wall, the electrons run across the wire, and then when I have something plugged in, they run into it, and then they go and they run the motor. Okay? Okay. Fun time. Turn in the book to page 162. Get your calculator. No, we're writing on our paper still. We're using our little formula. Yep. Okay. Kinetic energy equals 1/2 m. What's m?
Mass.
Times v. Okay. But what is velocity again?
The rate at how much it's going, the time of the distance. The rate of
Wait, are you looking for the definition?
No, velocity is 2 words.
Direction of times distance.
Speed and direction. So velocity is speed. So most of the time, they don't give you the word with a velocity. They give it to you as speed, and they just expect you to know that it goes here. Just remember, velocity is speed. In this case, we're going to use them in a way interchangeably. Okay? And then we have squared. Right? Okay? So before we ever start, let me show you something. You have your little calculator? Okay. Ready? Okay, I want you to type in 15 times 2 equals. Do whatever you got to do. What'd you get? Okay, now I want you to type in 15 times 15. What did you get? 225. There is a huge difference between 15 squared and 15 times 2. 15 squared means this number happens 2 times. 15 cubed means who does not understand? Does everybody understand? So when we're doing squared, it's not times 2. Got it? Awesome. We are going to calculate the green car on the page 162. What is the first thing that I have to do? Write the formula. KE equals 1/2 MB squared. Two letters are side by side, so we're going to multiply. Okay? The second step is to fill in the numbers. KE equals 1/2. Okay? Go to the picture. What's his M? No, the green car, genius. Kilograms. Times. What's his velocity, his speed?
15 meters a second.
Squared. No, the formula does. I'm copying from the formula. I just plugged the numbers in to where the letters are. That's all I did. Okay? According to order of operations, I have to do the exponent first because everything else is multiplication. Okay? So I'm going to take this right here and I'm going to do 15 squared. What does that mean I have to type in my calculator? 15 times 15. And what do you get? Meters per second. See how I did that? Now let's drop everything else down. So I just recopied the rest. Now everything gets multiplied, but y'all can't put this in. I can on mine, but you can't. So you're going to push 0.5 times 1,500 times 225 equals. Put it in your calculator. 0.5. What is a half? 0.5 times equals. Why are y'all looking at me weird? That's the correct answer. You think that number's crazy? Is that it? What's the deal? What are y'all thinking? Who's lost? Okay, where did I lose you? Multiplication? 0.5 times, look, instead of, you can't put, can you put this in? No, I can, you can't. So what is 1 over 2 in a decimal? 0.5. A half is 0.5. The parentheses, all these parentheses means I'm multiplying them. Times 1,500 times 225 equals.
I'll have to finish this.